Hello everyone, my name is Aditya Oak, and today I and my co-author Amir will present our work titled Language Support for Secure Software Development with Enclaves. This is joint work with our advisors Musard, Balliu and Guido Salvaneschi. I will begin by introducing Trusted Execution Environments, also known as TEEs. Trusted Execution Environment is a recent privacy-enhancing technology. In this, with the help of computer hardware, secure execution environments are created to perform private computations. These secure environments are also known as enclaves. Enclaves are protected from high privileged software such as the operating system and the hypervisor. Many hardware vendors today offer different implementations of TEE. For example, SGX from Intel, TrustZone from ARM, and Apple's platform security. This secure computing model is useful when a user needs to perform computations on their private data on untrusted third-party machines, for example, untrusted cloud hosts. This figure shows an application that uses this enclave technology. An application itself is partitioned into two parts. One part is kept inside the enclave, which usually contains some private code or data, and other part is kept outside the enclave. They communicate with each other via a dedicated interface. Integrating TEs with applications is not a trivial task. Here, a user needs to manually do the application partitioning, or they need to build the application in a partition manner from the start. Also, they need to design this enclave, non-enclave interface for communication. And the naive application partitioning may not always preserve the security guarantees. And this is a major concern, especially when the non-enclave environment is controlled by a powerful attacker. So instead of doing all these tasks manually with possible security issues, we can use the compiler itself to perform these tasks automatically and at the same time preserving security guarantees. So based on this solution, we present our programming model, JE. In JE, we present language-level abstractions to denote code placement and security attributes for data. The JE compiler automatically partitions the application into enclave and non-enclave parts. The JE also has a static type system for information flow control, and the static type system guarantees robustness in presence of active attackers. Now let us consider language-level abstractions provided in JE. We extend Java language with 5 language-level abstractions, which contain 3 annotations, enclave, gateway, and secret, and 2 methods, endorse and declassify. This snippet shows a simple password checker implemented in JE. It has 2 files, password checker and main. In password checker file, we can see 3 annotations. The first one is the enclave, which denotes that the class password checker is to be placed inside the enclave. The second annotation, secret, denotes that the field password is a secret field. And the third annotation, gateway, denotes that the method check password acts as a non-enclave-enclave interface. Methods endorse and declassify act as the standard information flow control endorse and declassify operators. The class main, which is not annotated by the annotation enclave, remains outside. This figure shows a high-level overview of JE programming model. The JE compiler accepts an unpartitioned JE code, and by analyzing the annotation, it partitions the program into 2 parts, one to be placed inside the enclave and one outside. We consider that the environment outside the enclave is controlled by a powerful attacker, and they can attack the enclave environment by changing the code and data in the non-enclave environment. Now I will hand over to Amir to present different attacker models considered in this work along with the type system.
Thank you. So when the outside of the enclave is under the control of stronger attackers, we have to consider attackers that can potentially modify the data and code memory outside of the enclave. And this sort of power for an attacker can cause serious issues, especially when dealing with sensitive operations such as endorsement or declassification. So we have to limit this attacker power. And what we should do is control the release of secret information, for example, declassification. And this process is called robustness. Robustness has been investigated before, but mostly for the decentralized systems. In our work, we just leave these definitions for robustness for two types of attackers. The first one is a data memory attacker, and the other one is a data and code memory attacker. So for the data memory attacker, it can control all of the data outside of the enclave and can change those, and particularly and most importantly, the parameters that are passed to a gateway. So in this password checker example, check password is a gateway, and the input of this gateway, guess, is coming from the attacker, potentially coming from the attacker. So guess is going to be a parameter of the gateway under the control of the attacker. To capture the effect of this attacker, we put holes outside of the enclave, and then we say that an attacker code that can modify the data memory can go into those holes. And then for defining robustness, we say that for all of the possible attacker codes, his observations should not change. So the parameters of the gateways are under the attacker's control, so they are untrusted. And these untrusted values should not affect declassification. So this password checker example should be rejected because the declassification at line 8 declassifies some untrusted value result. Our type system enforces this, and it ensures that declassification can only declassify trusted values, and declassification can only happen under trusted context. And theorem 1 proves that a well-typed program in our system is going to be robust under the data memory attacker. For the data and code memory attacker, it can change all of the data and code outside of the enclave. So in addition to the parameters of the gateway, it can also change the order and frequency of calling gateways. So for example, in this example, we have two gateways, bar and foo, and the attacker can call them in any order that he wants. If the original intention of the programmer was to call bar first and then foo second, and a data and code memory attacker can change this order and, for example, call foo and bar, and then it can lead to different declassification, and the attacker can learn more by just changing the order of gateway calls. So we define the program outside of the enclave under the control of the attacker as just a sequence of gateway calls, S prime. And this S prime, this sequence of gateway calls, models the attacker control over code memory. And we also still have the holes, which model the attacker's control over data memory. And robustness is defined, in this case, over all of the possible attack vectors that can go into the holes, and all of the possible S primes, all of the possible sequences of calling a gateway. And we also extend our type system to account for this attacker. We have to consider some restrictions to limit this attacker. And because we don't have enough time, I cannot go into detail for that, but we have theorem 2 in our paper that proves that with regard to those restrictions, a well-typed program is going to be robust against data and code memory attackers. In our type system, we also investigated some more features, such as endorsement or flow sensitivity, and also a feature we like to call delayed declassification, which is a result of declassifications not being immediately observable by the attacker. So we should keep track of these declassifications until they are returned to the outside. Now I hand over the presentation to Aditya to explain the implementation.
The JE workflow has two main phases. In the first phase, the JE compiler accepts the JE code and runs some initial security static analysis. In this analysis, we capture some security information, and based on this information, we convert the program into a GIF program. And then we use GIF compiler as a security verification backend. If the security verification succeeds, then in the second phase, we add enclave, non-enclave interface using Java RMI and split the code into two parts. For Enclave, we use Intel SGX, and we put a JVM inside the Intel SGX and run the Enclave code on top of it. And outside, we use a regular JVM. We evaluated our JE programming model with 3 case studies. First is the password checker that I showed earlier. The second is the updatable password checker, which is a different version of a password checker in which the password placed inside the Enclave can be modified from outside. And third test case was the medical data processing. In summary, we present JE, a programming model for secure programming with enclaves. We provide language level abstraction to denote code placement and data security attributes. We present JE type system, which defend against strong, realistic, non-enclave attackers. With this, we conclude our talk, and thank you for your attention.